and welcome back to Calero Academy. Today we are going to prove the law of sines, the law of cosines, and the altitude formulas. So let us do the altitude formulas first. Now, if we start off in a triangle ABC, in which if we draw an angle, we draw an altitude, and HA, in which A denotes the vertex point on which the altitude is drawn from, in which in this case is A. Okay, so in particular problems, trigonometric or geometric problems, when involving altitudes and triangles, it may be useful to actually know what the altitude formulas, and it actually is useful because we're going to use it to prove the law of sines. But let's stick to altitude formulas first. So altitude formula says that if beta, sine beta is equal to HA on C, then HA is equal to C sine beta. Now there are also more, because look, see, in this right triangle 2 here, sine of gamma is equal to HA on beta. So in this case, this is also equal to HA is also equal to B sine gamma. Okay, and so now there are more too, because you can see here, there are 3 altitudes in this triangle. We have just drawn 1 altitude, but in fact you can draw HB and HC. HC here, if you draw an altitude here, this is HC, and you draw an altitude B, and you will also get other formulas. And now I'll just pre-do it. And so first, if you start with HB as an altitude, if you start with HB as an altitude, you get that it's equal to C sine alpha, and it's equal to A sine gamma. And if you were to do it, make an altitude from C, in which this would be called HC, then HC would be equal to B sine alpha. You see, B sine alpha, and it would also be equal to A sine beta. If you see down here, this triangle here would be A times sine beta. Okay, so these are the altitude formulas, and depending on if you mix the sides around, you just use the same approach as I did, just using sine of this angle is equal to that and so forth. So the law of sines, those are the altitude formulas. Now the law of sines are derived from the altitude formulas, and so let's just consider, for example, HC. Okay, so HC is equal to A sine beta, which is equal to B sine alpha. So you can use here A sine beta is equal to B sine alpha. And so you get an interesting relationship if you divide the last 2 equal quantities by the product sine alpha sine beta. So if you divided both sides by sine alpha sine beta, you'd get that this is equal to A sine beta on so I'll write that down actually. A sine beta on sine alpha sine beta is equal to B sine alpha on sine alpha sine beta. And so you see, it's obvious that sine alpha cancel out, and here sine beta cancel out. So you'd be left with A on sine alpha is equal to B on sine beta. So this is really important because it relates 2 of the sides, but let's find the third side, since you can see. Let's find the third t that relates the third angle to the third side, which relates them all together actually. And so then let's take for example HB. Sorry for the stuttering. So if you take HB as using the same approach here, you get C sine alpha on sine alpha sine gamma is equal to A sine gamma on sine gamma sine alpha, and here gammas cancel out, and here sine alpha cancels out, and you're left with here C on sine gamma is equal to A on sine alpha. You see here, A on sine alpha is equal to C on sine gamma. Look, see here? So you can finally put them all together, and you get here that A on sine alpha is equal to B on sine beta, which is equal to C on sine gamma. And this is the law of sines. And it's really useful. This is really useful for solving triangles like this, where you have here 50, 70, and a side called 10. Obviously, this is equal to 60. And you normally using normal geometry, it's not possible using geometry, but using trigonometry and also what we just proved before, law of sines, you can actually solve it for this triangle or in many other triangles like that. Okay, now let's go to the law of cosines. Now, the law of cosines is a very old theorem. It's a generalization of the Pythagorean theorem. So if we move down, do we have enough space? Guess so. It's so small. Okay, so if we push this down here. Okay, now draw a line. This is the law of cosines. Okay, so it's not actually difficult to prove. You see here we have our triangle ABC. We draw the altitude H, and we have our sides A here and B, and this and P and Q, and C is equal to P plus Q. Okay, so now let's see. So the law of cosines says that B squared is equal to A squared plus C squared minus 2AC, product of those sides, times the cos of the included angle, in which this case is including this, including cos of B. Okay, so let's see here, in which case, sorry, this is actually, if you name this beta. So let's see here. Let's start to prove it. So from right triangle BDC, and if we name this B to D, just from right triangle BDC, what happens in here is that using our altitude formula up there, we get that in triangle BDC, we have that P is equal to stick in mind that P is equal to A cos B. This will be useful. And so now, using the Pythagorean theorem twice in triangles ACD, this triangle, and BCD, we have that B squared is equal to H squared plus Q squared, and which is equal to A squared minus P squared plus c minus p all squared. So you see here, yes, q squared. Okay, so you have now, so that b squared is equal to h squared plus q squared, which is equal to a squared minus p squared. Remember, you're using Pythagorean theorem in BCD to get that. H squared is equal to a squared minus p squared plus q squared, which is equal to c, the whole side here, minus p all squared, because it's q, of course. And so, yes, let's stop now. And then now we can simplify this and get that a squared plus c squared minus 2pc. Okay, so let's just bear in mind here that a squared plus c squared minus 2pc, because we we expanded c minus p all squared, and minus p squared canceled out with plus p squared, so we're left with this. And so b squared, I should write that there, and which is equal to then, so a squared plus c squared minus 2pc is equal to, well, before we move on, let's just remember that p, as we said up here, is equal to a cos b. So a squared plus c squared minus 2c times p, which is equal to a cos b. And so we can simplify this as equal to a squared plus c squared minus 2ac cos beta. I mean, sorry, not beta, I mean cos b. Or it's actually cos beta. Okay, so this is the law of cosines, as we've just proved in here. So law of cosines is really useful. Sorry, square box there. Because using the what do you call it? The law of cosines, you can figure out triangles like this. For example, here you have, this is 50 degrees, this is 12, and this 15, and this is x. Notice that this varies from the triangle up there. Okay, so you could use it to find triangles like this using C. This is your, turn it around, you get that this is your B, that's your A, and your C, so you could get x squared is equal to 15 squared plus C squared. I'll let you do that problem. Thank you for watching this Calero Academy video, and we hope this helps you with your trigonometric and trigonometry, and of course there'll be many more videos when I learn about half angles, double angles, and also a really troublesome question about some quadrilaterals and Apollonius's theorem. Certainly in the next videos we'll be doing the diagonals of a parallelogram is equal to d squared plus 1 plus d squared 2 is equal to 2 times x squared plus y squared. And next video we're doing area formulas, which is really interesting. And we'll be doing the for an arbitrary quadrilateral is equal to half d1 plus d2, which are the diagonals, times sine of alpha of the included angle between the diagonals. So thank you again for watching, and stay tuned for more Calero Academy videos.